Okay, let's analyze this satellite traveling around the Earth at some height h. And then that's the radius of the Earth, right? So this satellite there, when I show you an object, a box on a hill or whatever, there are two ways that you can analyze it. What are those two general ways? Okay, you could look at it and say observations, and when you look at it, mathematically, based on physics, you see a box on an incline. What are the two basic ways that you should begin to analyze that box? Number one, you do force diagrams. So you can analyze it by forces, right? And then, what else? What other way can you analyze it? That's straightforward, the easiest way to analyze it. Energy, right? That is it, right? The two ways that you try to do everything in physics is forces and energy. Actually, in the other order, energy then forces. Because forces can lead to kinematics, and kinematics are a pain in the rear. So you always want to look at things from an energy perspective first. So there's energy. So energy and forces are the two ways that you can analyze just about everything around us. So what I would like you to do is let's look at that satellite in terms of forces, okay? Now, so let's talk about this. Some of the forces on that satellite. What are some of the forces on that satellite? Oh, okay. The sum of the forces on that satellite equal what? Oh, I should call people directly. Hang on. So the sum of the forces on this are ma sub c. And what does the sub c stand for? Centripetal. Or meaning center seeking. That there is some acceleration on this satellite that's making it move in a circle. Does anything naturally want to move in a circle? No, never, anywhere, at any time do things naturally move in a circle. They're always moved in a circle by something else. Now, Kenny, what is the thing moving this in a circle? Gravity. So does everybody here see that Fg is equal to ma sub c? Does that make sense? Okay? So then, Hector, what is the equation for gravity, for the force of gravity as per Newton's universal law of gravitation? This is also on your formula sheet. What's that? In this case, is there a big string holding this thing around the Earth? No, so there can't be a tension. Look on your formula sheet. Okay, Hector is exactly correct. Does everybody see this? The force of gravity. It can be mg, but in terms of the universal force of gravity, or what we're talking about here is the force of gravity between two objects. It's big G, m1, m2 over r squared. Yes? Does this make sense to you? That is Newton's universal law of gravitation, or law of whatever. Yeah.
So what's that number about that constant? 6.6.
Yes, that is G. 6.67 times 10 to the minus 11 newtons meter square per kilogram squared. Yes, Tiffany.
Is the negative, can it be changed back and forth or no?
Yeah, okay. Tiffany raises a good question. What about the negative? Because there's technically supposed to be a negative there. That negative is to explain something. The way I look at it, okay, it comes out from the calculus and it comes out from the nature of positive work, okay? If something is falling towards you, how do you do work on that thing? Or something's moving towards you. Well, let's say a shopping cart's rolling towards you. How do you do work on that? Yeah, you push it, and you're pushing it away from you, right? But then, so that we understand that to be work, right? So basically, when something is coming towards you, right? That's like negative direction, and away from you is positive direction. So gravity pulls things towards you. Therefore, gravity is negative. Does that make sense to everyone? Right? That's why there's a negative there. And then if we're talking about, let's talk about potential energy, UG, right? Right underneath F sub G on our formula sheet, right? That has the equation again. And the only difference between F sub G And U sub G is what? Marilyn. What's the only difference between those two equations? It's on your formal sheet. I didn't write it. Yeah, R, right? Because basically what we've said is energy is force times distance. Well, if force is blah, blah, blah over R squared, and you multiply that by R, R's cancel. And you're left with just the potential energy. So the potential energy between two planets or something, where is it zero? Where do you, okay, let's go with Kate. If you're an astronaut, you're in a spaceship, okay? So Kate is going to be the first interstellar astronaut from Earth. Okay, where does she need to go to have zero potential energy between her and the Earth? Does she have zero if she's on ground? But do you see why this is confusing? When we have talked about gravitation, we've talked about potential energy due to gravity all the time. And what was that formula? mgh. So where is zero potential? On the ground. And where is more potential? Up in the air. But actually, what we've been doing this whole time, when we said, is it recording? I think it's recording. Okay. All right. Well, anyways, so if we use forces on this, right, then we're going to say, so what I want you to do is I want you to take big G, M1, and let's call M1 the mass of the Earth, and M2 is going to be mass of the satellite, equals MA sub C. And remember, what does A sub C equal? V squared over R. So this is going to be mass of the satellite times V squared over R. Okay, set those two equal to each other. Yeah, so that's from right here. The H is from me saying this is this height above the Earth. So the R, right, in this equation is the distance between the two centers of the objects. So then that R, as Tiffany mentioned, is just this whole thing. So this right there is that R. Okay, so that is what we get when we compare forces. Forces allow us to see the geosynchronous orbit. So if you send your satellite up to space, you put around, park it right over wherever you want to park it, and then you make sure that it has this velocity, square root of big G, M over R, whatever, that lets that satellite stay directly above. And this is what, if you have Dish Network, if you have DirecTV, that's what's happening. Those satellites are, let me think, where's my room? That's San Gabriel, that's north, that's south, about there. They're about over there, right? If you've ever had to point your satellite dish, then you turn it and then you gotta watch TV and it goes, and then when you hit the right spot, yeah, it's a giant pain in the butt. But anyways, they are sitting in geosynchronous orbit. So now with forces, now let's go ahead and do this with energy. If I wanted to kick a soccer ball up to a given height above the Earth of h, so the same similar sort of idea, here's my soccer ball. I want to kick my soccer ball up to a height of h. Obviously there's RE. Then in order to get it to stay there, what velocity does it need to have? Right? So now I'm talking about an object that's moving, and then I'm talking about that object is going to be staying some height above the Earth. Right? So instead of forces now, you're going to use energy. That was the other system. So use energy. Go. The initial kinetic energy that you give is going to equal to the ultimate gravitational potential energy that that thing has. All right, so Betty, what's kinetic energy? Okay, mv squared, right? Okay. Now we have, this is going to be the mass of the ball, right? Because we kicked the soccer ball. Now, if we want that soccer ball to be at a certain distance up in the air, what will be the potential energy? Universal law of gravitation. Big G. Okay, we're going to say mass of the Earth, mass of the ball, over R, and it's going to be that plus H. Okay, does this make sense? Because it's potential energy, not force. Okay, did everybody catch that? This is not over R squared, because this is the potential energy. This is not the force. So, I can now cancel the mass of the ball, right? And then I can say V is equal to the square root of 2G ME over RE plus H. Now, wait a minute. What does that look like? Doesn't that look... This thing that you're looking at is called... this is this geosynchronous orbit speed. Right? This is what's needed to keep a satellite in a specific position over the Earth as it goes around. Yeah.
Oh, can you just, for like, because you know how you draw like the R and the H, can you just put them as one big R?
Yeah, you can just do that. Like if you just put that as R and then you have as a subscript R is equal to RE plus H, that's fine. Or if you just literally in a problem added up the numbers, that's fine too. Okay, questions? Everybody go with this? Yeah. Very similar to this. The only difference is the square root of 2. So, escape velocity is around 1.4 times bigger than orbital velocity. And of course, if you wanted, escape velocity just gets the ball up to that point, right? If you want to now orbit around the Earth, you would have to give it extra energy once it's up there so that it will not eventually fall back down. Okay, questions? Yeah. Why is there an R squared on the forces?
Yeah, for the G formula.
Oh, for the universal gravitation? Okay. Okay, let's see. When we said MGH equals PEG, this term, MGH, is actually delta PEG. It's the difference in gravitational energies between two places. So if you have a box that's on Earth, and then you raise that box up to a height h, right? Does it make sense to you that that box on Earth, right here, it has a PEG? Because the box and the Earth do not share the same center, right? They're separated, the centers of mass, the centers of those two objects are separated by the radius of the Earth. And how would you know this is true? Because if I could make the ground underneath the box disappear, would it fall? Yes, of course. So there still must be some force of gravity that creates a potential energy between it and the Earth. So what we're actually doing when we say MGH is PEG, we're actually saying MGH is equal to the difference in those two, in the potential energies here and the potential energy there, PG1, PG2. All right, so that's that term. So when we talk, yeah, this works like, kind of like if I took a rubber band and I could stretch that rubber band 30 centimeters. But then I stick a piece of wood inside the stretched rubber band that's 20 centimeters long. When I let go, do you see the rubber band's only going to snap 10 centimeters? I'm not going to get the full amount of energy. So there's the difference in energy between the full stretch at 30 and the partial stretch of 20, because it's stuck on the wood. The difference is the MGH that we've been using this whole time. Okay, well, I hope that makes sense. Anyways. term, when we talk about this term, we are talking about the absolute potential energy between two celestial bodies, two things that are floating in space. So this works like a big rubber band connecting the two centers, right?